Okay, so talked about a bunch of this stuff now. Let's kind of flip back. So at the very beginning tonight, we started talking about memory, and we're kind of talking about maybe the history of memory to a certain point. So we mentioned floppy disks. We threw zip drives in there. I mentioned the jazz drive. Let's leave that out for a second. What's kind of our next? Maybe we have CD-ROM, CD drive. So we might say CD/DVD. Call them similar speeds. In the very early day of CD drives, you had a 1x CD drive, then a 2x, and an 8x, and a 10x, and a 12x, and then 24x. And I think it went up to like 54x or something like that. And then they just stopped. They stopped putting the number on it. It was just a CD drive. But let's just call them relatively the same speed, relatively slow compared to other memory, but fast compared to a floppy disk. All right. Now, is everybody in here, we've burned a CD or a DVD at some point? You actually written to a DVD? Okay. So what's kind of next in our pecking order? Probably our hard disk drives. All right, so these guys are a mechanical technology, right? Okay, with disks, spinning disks and layers and stuff like that. All right, then what comes next? Probably an SSD. Okay, so we could say SSD, and maybe we also throw in here flash memory. It's kind of they're the same technology. Now it's just a matter of putting more stuff in the same spot and giving it a fast enough interface to make good things happen. All right, so SSD, flash memory, however you want to think about it. Now we'll get into the stuff that we're really talking about today. Because remember, this whole conversation started by me asking him how much memory is in your computer, right? And he said 16 gigs. And I said, well, what are some other reasonable answers to that? All right, so after we get past our hard drives, what's our next fastest memory? RAM. Okay, so I'll call that RAM, and we're gonna really talk about this quite a bit today. So we're gonna explode that out to what it actually comes down to. What's after RAM?
Cache.
Okay, good, perfect. Were you looking at the book? All right, okay. Because the book talks about these things together. So next thing is the generic term cache. We're going to talk about that a lot today. So the rest of today is going to be a discussion of RAM and cache. Those two things. Technologies related to RAM, less so about the technology related to cache and more about how cache works. Okay? And then I'll have you go through the book to kind of fill in the details of some of those things. So I want to talk about it at the high level so we can get the conceptual stuff, how this works. So RAM cache, what's after cache? Yeah, then our register. All right. So let's leave this list at this. So this goes in. This is the slowest memory up top here, and this is the fastest memory on the bottom here. Okay, so now let's kind of, if we're talking about RAM, just want to talk about RAM at the high level. So now we've replaced that generic term memory with, when I asked you the question, how much memory is in your computer, and you translate it to RAM, now we're talking about RAM. Okay, so we think of RAM as being relatively fast in the big scheme of things, right? But certainly not the fastest. It was, a little bit lower than halfway through our list, something like that. It's fast, but not that fast. What's the role of RAM in our computers? Okay, so it holds instructions. So yeah, I think that's a good one. Holds instructions in such a way that it is ready to be loaded onto the CPU-ish. There's maybe some steps in the middle there, but something along those lines. So generally speaking, we move stuff, you say it loads the program. So we move stuff off the hard drive into RAM. Okay? Now when we do that, do we move all the stuff off the hard drive into RAM? So if you have a program whose install is 1 gigabyte, when you double click on that program, does it load the entire 1 gigabyte of instructions into RAM? What does it do? So loading a program. When we double click on our icon for Photoshop or something like that, what's actually happening under the hood?
There's a loading in each slice.
There's a loader program.
There's a what?
There's a loader program.
Okay. So, and what, just generically speaking, what's happening with that loader program? What's ultimately making it into memory? A small portion of Photoshop? Okay. Now which portion? There's that loader program we're talking about. There's going to be some starting point for the application, right? And that's going to kind of be the catalyst that gets some more stuff pulled into memory. But you're not going to load the entire program into memory. Every single time you open up an application, do you use every single feature in that application? So a lot of times you're loading stuff on demand, right? Okay, so I mean, there's menus in Microsoft Word you've probably never touched, right? So those menus likely have never been loaded into RAM on your computer, but you still paid for it, unless you download it off of BitTorrent. Okay, so there's going to be a portion of the program loaded into memory. From our perspective, that's good enough, because this is at that point where now we're talking about an operating system concept, right? Okay, we want to focus on the memory component of this. So a portion of the program is loaded into real memory. Now, a portion of the program is also loaded into what? We have real memory. What other kind of non-real memory do we have? So we have something called virtual memory. So a portion is loaded into real memory. It might be fair to say the rest, but let's just say a portion, because it isn't necessarily the rest. A portion, probably a larger portion, is loaded into virtual memory. What is virtual memory? What is that guy? That didn't make your list. A couple slides ago, we had different kinds of memory. Virtual memory didn't make your list. What is virtual memory? Did you lose that with the PCI Express slots?
Yep.
Same place. Same place. Burn it up in reentry. We've all heard of virtual memory before, right? And something you've heard me say lots of times in classes is that one of the things with technology is you have a lot of these kind of buzzwords that float around, and most of them mean easy things, right? But who can remember all the stuff besides me? I don't know all this stuff. It would be interesting to have a real life measurement of like how much stuff one has forgotten, right? Because eventually, I mean, it's just a time in thing, right? You know, you just been on Earth longer, you've heard more things, but then you miss new things, right? Because there's like the sayings that the young folk have today that I miss. Like did I tell you the story before of I think this was maybe 2 years ago, something like that. 3 years ago, somewhere in that ballpark. I had a first level programming class, and I made some comment in class, something along the lines of Netflix and chill. I didn't know what it meant, but I think I said, I think I'll just go home and chill and watch Netflix. I think I said it like that. I didn't say the phrase, but then they all start giggling. And I'm like, well, what's so funny? So then they explained to me the concept. So it was kind of funny.
Do you know what next week? Chill and Edwin?
You'll have to tell Edwin later. But it was. It doesn't mean watch Netflix and chill. It means something else. Yeah. So they.
So you can't talk about it.
And I'm recording, but it means something else. Ask your friends. But yeah, in any case, it was kind of funny because when I first started teaching, I was the same age as a lot of my students. So I knew the lingo, right? And I still feel like I'm what is it? I'm hip, right? I still feel that I know I think I'm more in touch with the younger students than maybe a lot of faculty might be, right? But I'm starting to notice that there's new things that I'm missing. I just, right over my head, just missing the stuff. All right, so virtual memory. What is this guy? We got to kind of think back where this came from. We've had the discussion in here before. We're going to discuss it some more today. Not as much detail because we've already talked about it some, but memory used to be really expensive, right? Okay, so you mentioned that you have 16 gigs of RAM in your laptop, correct? I mean, that's a good amount of RAM in any machine, right? Maybe you find some computers today that have 32 gigs of RAM. I mean, we're talking about personal computers. You can find servers that have more, but 16 gigs would be considered a relatively high amount of memory for like a professional level computer today. Most people either have maybe 8 gigs or 4 gigs of memory in their computers. Okay, so we throw these terms around today like it's no big deal. Okay. 16 gigabytes of RAM years ago would have been millions and millions and millions of dollars. Just ridiculous money. I mean, it was like a number somebody would throw out to just say as a joke, like, oh, I have this much memory. Kind of like today we would say, we have a I don't know, 450 million megabit per second internet connection, right? We're just picking this number out of the sky that just seems completely implausible. Yet at some point in time, we're not even going to think about the speed of our internet. Just, it's the internet. It's instant. It's the same speed as if you had a local hard drive. It's the same. All right, so we won't think about speed anymore. All right, but so there was a time when 16 gigabytes was a joke, but now you just kind of announce it, passively. I mean, it doesn't make you that special having 16 gigabytes. Who else in here has 16 gigabytes of RAM in their computer right now? Okay, so almost half the class in here has 16 gigs of RAM in their machines. Right? Now, 16 gigs of RAM is pretty good. How many of you have 8? You think? You're not even sure?
Yeah. I was sure about the gas. Yeah, and I did not say yes for 16. So.
But are you sure about that?
Yes, I know.
See, I think that's something else that's changed. So when I came through school, it seemed like it was, and maybe this has to do with maybe almost something I said a few minutes ago with eventually the internet will just be the internet. We don't think about the speed. And I think some of that maybe has happened today, right? Where, years ago, I mean, most people in technology, any computer science major, they would know like the specs of their machine. They would know the bus speed. I mean, you would know everything about what was in your computer. Just common knowledge. And maybe it's because it's easy for me to immediately categorize that as like, well, they cared more or something like that. You young folk, you don't even know what you're missing. You should know how fast this, that, and the next thing is. But the reality is maybe it means it's less important today. I mean, back then there was legitimate compatibility things you had to deal with on a daily basis. You had to go into a machine. If you went into a computer lab with a floppy disk, you had to make sure that the machine, that it was formatted to work in the machine that you were about to use. Now you just stick the USB drive in and it works. You don't think about it. It's not a problem anymore. So a lot of things that used to be just part of your daily problem solving have now disappeared. And now it's been replaced with other things, right? So there's other things that, you do know a lot about the detail aspect of it that didn't even exist years ago. Because you don't need to know that your computer has 16 or 8 or however many gigabytes of RAM. You just know it has enough. Or it doesn't have enough. We kind of have that categorization. Either my machine is good enough or my machine really isn't good enough. That makes sense? Where we don't maybe know the details. But in here we care about the details. All right, so we should know the details. So back to virtual memory, we're here talking about Memory used to be really expensive. Fair enough? All right, so since it used to be really expensive, it would make sense that at some point in time we maybe wanted to augment our physical RAM with some additional, we'll call it fake RAM, to make our computer function as if it had more RAM. That make sense? Because really, when we think about memory, and this is kind of where I'm going with this, when we go back to this idea of memory, memory is one of many resources inside of our computer that we're sharing, right? That's how we talked about CPUs. That's how we're talking about all these things. It's a resource, and that resource gets shared by different things, and memory is one of these resources, and it's a resource that, as you point out, stores, and I don't actually think it is an oversimplification. It stores the instructions that ultimately the CPU will eat, right? All right, so, and we put it there because we think of memory as being relatively fast. We think of RAM as being relatively fast. All right? So virtual memory, what it does is it takes a portion of your hard drive. So this guy takes a portion of the hard drive, or I guess more modernly, it might be your solid, your SSD, but your hard drive. So let's just say that. Hard drive rather than attach the technology to it. And sets it aside to be used as additional RAM.
So essentially, virtual memory is a lot slower.
It's a lot slower. Yeah. So, lot slower than RAM. I think that sums it up. Okay, because you're now using your hard drive. You could only be so lucky that it's an SSD. Then it's only much slower instead of much slower. All right, it scales. Once you go down to those mechanical hard drives, things are getting pretty hit and miss, pretty shoddy, pun intended. Aha. That's how you pronounce her name, right?
Uh-huh.
Ha! Ha! Do you know that? Did you get that joke? His last name is Shoddy. Is it the first time you're meeting him?
Why is it called virtual? Is it because it seems to reside in main memory and depends on secondary?
Yeah, as far as the operating system is concerned, it thinks it's memory because it actually acts like memory. Because when we use system RAM is a resource, and it's a resource that data moves in and out of at a certain speed. Okay? Hard drives are a resource. Data moves in and out of those hard drives at a certain speed. Now, traditionally, when we were applying a file system to a hard drive, we're using that data storage, those data storage buckets, in a very specific way. When you set aside some of your hard drive for virtual memory, instead of applying a file system to that, you're treating that portion of your hard drive the exact same way as you would read and write to RAM. Okay, so you're no longer writing stuff to it as a file system that have a directory structure and all this stuff. Now you're treating it as if it's buckets of RAM. So you're using that resource in the identical way as you would use system RAM. It just happens to be accepting and giving you data at a much slower rate. All right, so as far as the operating system is concerned, it's RAM. It's just crappy RAM because it's got to wait for results. Right? So we do want to minimize the amount of stuff we do store in virtual memory, but we go back here, we mentioned that a portion of a program is loaded into real memory. Hopefully the portion that we think we're going to need soon. Okay? Similarly, a portion will be loaded into virtual memory. That's going to be a portion that we think we're going to need less soon. All right? Now, the management of that, this is an operating system task. All right? So this is process scheduling, and a lot of times virtual memory, you've maybe heard of this as being called, I don't know if it's fair to really call this a synonym, but I think it's often used this way. Swap space. Yeah, virtual memory is often referred to as swap space. All right, because what it's doing is it's kind of holding things that you might need soon in a in a format that looks like RAM. And when you try to look up something, so when we talk about how memory management works, again, this is an operating system concept. Most of our memory management algorithms today, the modern one is a paging memory management algorithm. So when we go and look for a page in RAM and we don't find it, okay, we get an exception. Okay, and then what do? We need to go and retrieve the actual page. So we find the page in virtual memory and we swap it in, hence swap space. All right, so we first look for it in the fast memory. When we don't find it there, then we look for it in slow memory and move it into fast memory, swapping out something else from fast memory. Make sense? That we don't think we're going to need soon. So again, the process of figuring out what's okay to swap out, what's not okay to swap out, that's all operating system stuff. Okay, that's the whole memory management aspect of the operating system, trying to be as efficient as possible. Make sense? So we don't care about those details. We do as a computer scientist, but not from a computer architecture perspective. Okay, but we do care about the memory aspect of itself, and we're talking about the different types right now. Okay, so one way or another, okay, our instructions end up getting to the CPU. All right, and their diving board to the CPU starts off in true system RAM. So if it resided in virtual memory for a period of time, it is, from our perspective, magically swapped in by the operating system's memory manager, hopefully using, a reasonable algorithm that we're, because you can run into the situation where you're constantly swapping. Because the next page you need is actually the page you just swapped out, which is the next page you need, and so on and so forth. Anybody remember what that's called? When you're in a constant state of swapping, almost like an infinite loop. You would have had it in probably your operating systems class. Starts with a T. H.
No. Oh no, that gives the
R. A. Thrashing. It's thrashing. Okay, so thrashing is when you effectively have this, it's called infinite loop of swapping. Okay, so in that particular case, you would, a couple things are going on there. Either it's a really bad algorithm, or you just flat out don't have enough RAM. If you don't have enough RAM and you're using an immense amount of virtual memory to make up for that fact, and you run into a lot of thrashing problems, you just need to buy more RAM. That's what you need. There was an interesting problem I had when I was, I think it was in grad school, in an operating system in operating systems class in grad school, where there's actually, and I don't remember the exact problem, but there's more memory isn't always better. There's actually was a math problem that we solved where you could actually create a thrashing scenario with less RAM. With more RAM than if you had less RAM. It was one of those kind of trick things. Like the numbers just happened to work out based on a common memory management algorithm. That given memory of a certain size, it just happened, like bumping from 6 to 8 gigabytes, something like that. It was probably less than that, but let's just say that actually hurt you in that one scenario. So it was kind of an interesting trivia type thing. But bottom line is, if your computer is thrashing a lot, you need more RAM. Makes sense? I mean, this shouldn't really be a major issue with modern equipment today because memory's become a lot less expensive. But you do still see it in some students' computers because some of, again, we go back to students typically don't have this abundance of money sitting around. So sometimes they have a handed down laptop that, even though they're in the modern era, is not from the so modern era. It's from like a couple of weeks ago, right? It's a little bit older, but that's kind of the punchline there. But from our perspective, virtual memory is hard drive space that acts like RAM. We're going to call it really, really, really slow. It's probably really going to be the last time we're going to talk about it. But we're going to jump over to actual RAM technologies now. Okay? So, and for the next several minutes, I want us to really consider RAM to be a resource that our computer uses. Okay? So let's kind of create a slide here called
I wonder why data was not there. Only in previous time. Why only instructions? Why not data?
It is data. It's instructions and data. You said instructions.
I told data was good. You did not include.
Oh, I didn't let you finish. All right. So what I want to think about here is RAM as a resource, RAM as a shared resource in our computers. Okay? Because this is when the rubber really hits the road for us. We can think that 16 gigabytes of RAM is enough. But typically when we think about RAM today, we're thinking about capacity. But capacity is not our problem anymore. Now we really have to think about the speed of that RAM. That actually becomes our new bottleneck. And it becomes even a bigger bottleneck as we kind of move through this. So I'm going to think that's what we're going to talk about here. So RAM as a resource. Okay? Who uses RAM in our computer?
CPU.
Process.
Okay. Yeah, CPU, processors. Is that it?
Oh, no. Your hard drive does and accesses it.
Yeah, so I mean, is it fair to say that many components, either directly or indirectly in the computer, share this RAM resource?
Yes.
Okay? Even if we just think about it from a processor perspective, which is, I think, the obvious perspective, right? So we're going to think about a processor shares that resource, which is RAM. So let's roll back in time and think about well, here, I'm going to pause this. I brought up a website here that kind of just goes through the history of RAM. And we're going to kind of pick some newer things from there, but we're going to look at some speeds. All right, because the speeds are more important, not so much how fast DDR3 is versus DDR2. What we're going to really care about here in our discussion is going to be how fast RAM is, the clock speed of RAM, let's say, relative to the clock speed of the CPU. All right? Punchline for us right now, the foreshadowing piece of this is our CPUs today are operating at a higher clock speed than our RAM today.
Has it always been that way?
Not always.
Okay.
Not always. But back then the CPUs were a lot slower. So we had other problems. We had the slower CPU problem, we had not enough RAM problem, we had all sorts of problems.
Well, isn't that interesting then? Do you think at a certain point where the CPU would actually start running, wouldn't be able to go much faster? Because you were saying earlier in the semester, like, they can't pack much more into those small chips.
Good point.
So essentially, they're kind of like, they're hitting the top.
Okay, so you're saying that at some point is the RAM going to pass it?
Yeah.
Okay, I'm going to have you answer that for me in a few minutes.
Oh.
All right?
Yeah.
All right, because that's, I mean, what you're getting at there is exactly where we're going. Okay, because we want to think about RAM as a resource, and we want to think about how that resource is being used and who is using it. All right, so I'm going to pause this for a second. Let's just go back and I just want to go through this. I brought it up before class started. History of memory. Okay, so we could go way back. This is what RAM looked like. Okay, you'd have a little 16-byte or piece of chip that you would stick in. You have a whole bunch of these guys linked together. These are the pinouts for it. Relatively unimportant. See them in a museum, whatever. You can probably go out there and see some things like this hung on our wall. I think Dr. Locklear spells computer science down the hallway with some old boards. Okay, so you could probably find some stuff that looks kind of like this, and these would actually be double stacked. So you'd see them two stacked on top of each other is how they were a lot of times stored on boards. Unimportant for us in here. This is more of a museum piece type of appreciation. Okay? So kind of scroll through this. All right, so SRAM, DRAM. So this has to do with single-sided versus double-sided. All right, whether your chips are all on one side versus your chips being on both sides of the thing. Make sense? All right. More chips, more RAM. All right. Fair enough. Easy enough thing to come to the conclusion, right? All right. More chips, more RAM. So kind of we're talking about where our technology came from. Keep spinning through down here. We talked about asynchronous versus synchronous type stuff. Different read and write speeds. So you might read from it at one speed. You might write to it at a different speed. We understand those two concepts now. We don't care about the specific technology that these guys might be, how it applies to it. Like, oh, well, this particular technology was had this synchronous speed, and this other one was this fast for reads, this fast for writes. But you've seen this in practice, right? Sometimes you'll see, you'll see the specs on like the latest M2 SSD drive, solid state drive, and you'll have a read and write speed, right? And those are sometimes different speeds. That memory actually ends up acting synchronously because the way to read from it is different than the way you write to the disk. Make sense? They have different speeds. Synchronous versus asynchronous, that's fine. We understand the concept. Okay? SDRAM, single data rate. SDRAM, we have a newer version of this, which was double data rate, DDR, right? So our original SDRAM before DDR memory was single data rate. Then it became twice as fast in terms of the data rate with DDR memory. All right, data rate's kind of the piece that we're getting to here, the speed of a memory. When you were shopping for your parts for your new computer, you said you got DDR3 or DDR4?
DDR4.
Okay, DDR4, and it had some megahertz rating next to it, right? Do you remember what it was? Yeah, my guess is, I think DDR3. Is DDR3 the 1600 megahertz? So maybe DDR4 is 2200 megahertz or something like that?
Let's see. $3,000.
3000 megahertz?
Mm-hmm.
Okay, fair enough. All right, yeah, here, I see 3200 megahertz, whatever. Oh, yeah, does boosting DDR4 to 3200 megahertz. Okay, so 3 gigahertz,
Yeah.
call it that speed. So we'll come back to that. We'll use that 3 gigahertz number. I might actually want our examples a little bit lower than that just to really drive it home, but 3 gigahertz is fine because 3 gigahertz is going to allow you to answer the question I told you to answer.
Okay.
All right, in fact, oh yeah, we're going to use 3 gigahertz, okay, because that's going to show how well you understand the concept in a few minutes. All right. Okay, so, I'm sorry. Go back to my slide here. All right, so we had DDR, and then we go to DDR2. Still double data rate. It's not twice as fast, but we're upping the clock speed. All right. Better RAM. One thing we haven't necessarily seen recently is, I guess we've seen it to a little extent, but it's not like a real consumer-facing change, is you could get 4 gigabyte sticks in DDR, in DDR2, in DDR3, in DDR4, right? The capacity of our memory hasn't necessarily drastically changed recently, correct? I think that, we do have some technology out there that allows us to have, I think, 16 gigabyte. I think even, who makes it? Is it Samsung that makes the 64 gigabyte sticks? But I mean, those are not consumer grade stuff, right? So, but the punchline is that you would get like an 8 gigabyte DDR3 or DDR4 memory stick. So in your new machine, did you do 16 in your new machine? So you have 2 8 gigabyte sticks? Okay. So, and you paid whatever, $70 or $80 per stick, whatever it was. So, punchline is that we haven't necessarily seen the capacity of our RAM sticks change drastically over the last several years. What we have seen is that megahertz number after it. Okay, that number keeps going up. Okay, so we want to think about that here in a minute. All right, so DDR3, DDR4, probably next year we're gonna have DDR5. Actually, is DDR5 the one that's currently in on graphics cards, or is it not a thing yet?
Yeah, that's on graphics.
Okay, but whatever. The point is we're just gonna keep adding on the DDs until we finally come up with a new technology. Whatever. Okay, but what we want to focus on here is we have this concept of memory, however that's being fabricated. Whether it's DDR2, DDR3, DDR4, it doesn't matter. It does matter for performance. But the way our CPU interacts with that is going to be the same because it's relative to that number. Okay, that 3,000, let's use that 3,000 megahertz or the 3 gigahertz number. All right, so you had DDR4, right? And we're going to say that was at 3,000 megahertz. All right, and I'll put a little parentheses here. This is essentially 3 gigahertz-ish. Okay? Now, what is the fastest that a CPU can read from a 3,000 or a 3 gigahertz DDR4 chip?
Well, what's the fastest the CPU operates on?
We're back to our modem example, aren't we?
Yeah, it's
Okay.
as fast as it can be.
Who would have thought this would be similar to old dial-up modems? Okay. The fastest we can communicate between RAM and the CPU is the slower of the two, right? Now, most of the time, up until we can call it recently, but even recently, most of the time our CPU is quicker, and for a long time our CPUs were a lot quicker. Okay, think about the clock speed on our CPUs today. What's the fastest clock speed of a CPU you kind of know about today? Maybe 4.2, something like that. Yeah, and that's like turbo boosted or something like that, right? Okay, let's just use 4 as our example. So we're going to call 4 gigahertz like a really fast CPU today. What would a really fast CPU have been 4 years ago?
You mean like price-wise?
No. Speed.
Still, probably slower. Well, you wouldn't be able to do as much because the RAM wasn't as fast.
Now forget about that. I'm just talking about CPUs. A fast CPU today is 4 gigahertz. What was the fastest CPU 4 years ago?
3, 2 or something. 1.
Probably about 4.
Really?
It has not substantially changed.
Really?
Yeah. The actual clock speed of our CPUs, I mean, we might have some ability to turbo boost to maybe a little bit faster today, eking out a couple extra miles per hour if you're thinking about this like in car terms or something like that. But generally speaking, we have not noticed a drastic increase in clock speed on our CPUs over the last many years. We've noticed some other changes in our CPUs that we'll talk about, but not in clock speed. We kind of we've hit a wall. Why do you think we've hit that wall?
Is it because of the connections? We can't cram any more stuff in there without like.
Oh no, because we're definitely putting more stuff in there.
Okay.
Now we're fitting more stuff on the CPU. They're just not getting the clock speed's not any faster. So how fast we can, let's just say, read and write from the CPU isn't any faster. The capabilities of it might be faster or might be better, more vast. But the maximum speed that we can read or write from it hasn't drastically changed. Why do you think that is? There's probably several reasons, but I think there's one really big reason. One word, starts with an H. Heat.
Okay. I would guess that.
Yeah. I mean, I think at the end of the day, almost everything that's dealing with our modern, because at this point we're dealing with silicon-based hardware, we're at a heat problem at this point, right? So everything's about, now we have machines with liquid cooling and all this stuff. Now it's a matter of how can we fight heat. Now we've gotten pretty good at that, But that's, I think, one of the main reasons why we haven't seen clock speeds drastically jump. Is because now we're at a point where to drastically jump the clock speed, A, we have to say, is that necessary to do what we want to do with our computers? And B, is it worth the heat? Because what you would probably have to do is you'd have to, A, redesign the chip, probably have a bigger chip to dissipate across, and you'd have to really focus on the cooling technology.
Do you think that's going to happen?
I actually don't, because I think what will happen is the way we approach computing will change.
Just overall.
Yeah, I think, and I mean, this has happened before. I mean, this kind of goes back to the argument when we talk about, will Microsoft Windows ever lose its dominance in desktop operating systems? I think the answer is no, because we're moving away from desktop operating systems.
Okay, I was going to say, well, no, unless they completely change the system up that Microsoft.
That's it. Microsoft does.
Right.
So Microsoft doesn't compete
They're-
truly in the mobile space.
Right.
So I think there's a pretty decent chance that we might see something along the lines of an iOS or an Android becoming more of the standard laptop OS, because we're moving more towards those guys being our productivity tools than our traditional operating systems. But at the same time, those operating systems are going to have to evolve to pick up the slack for the things they can't currently do that you can do on like a Windows. Yeah, so I mean, this kind of happens in anything, right? You get to a point, and then all of a sudden there's a modification in how you're accomplishing the task, and there's a bridge between those two things where the road might be a little rocky, but eventually then you're on the new track, and then you're going in places with that. So I mean, I think heat for a long time might continue to be an issue, but I think the issue will change. I think we'll kind of almost have a reset, and then work our way back up to too much heat or something like that.
It doesn't last long when with heat. My brain have built the last 2 years, 77 K, 77000K.
Yep.
i7 gen.
The fan died, CPU fried.
CPU fry and after 2 years.
Yeah. So I mean, the punchline is that heat's the issue, but that doesn't matter, because right now, usually we're not talking about, oh, my CPU is too slow. If you had a CPU from 3 years ago, and it was a pretty good CPU from 3 years ago, it's probably still pretty good today, right? There might be certain tasks that it hasn't been optimized for. When you look at the Core i7s, the 6600 versus the 7700 series, you might see the identical clock rating, and those two processors actually might perform identically for a huge percentage of tasks. But then there's going to be those couple of tasks that have been optimized on the 7700 series that it'll outperform the 6600 series. And that's where Intel will say it's up to 40% faster or something like that, right? It's not across the board 40% faster. It's those three things. Okay, if you're doing one of those three things, you're going to benefit from this. If you're not, well, we want you to still give us your money. That type of thing. But that's okay. For me right now, what I want us to focus on is that, let's just use that number, that 4 gigahertz number. Okay? Doesn't matter when your CPU came out. Doesn't matter what CPU it is. Its clock speed is 4 gigahertz. Okay? So you have something that can read from memory at 4 gigahertz. All right? So we're going to say CPU at 4 gigahertz. And it's going to communicate directly with RAM and RAM can communicate at 3 gigahertz in our example here, right? So what's the maximum speed we can read and write between the two? 3. Now, presumably, since we're dealing with digital logic, there is a physical distance between those two, but not that far, right? The motherboard, you're 6 inches or something like that. There's a physical distance, but it's not that huge. So that's going to add some overhead. The time it takes to drive that road. We'll slow it down a little bit. But because we're dealing with digital technology and we're not dealing with line noise and stuff like that, we can assume we're going to get. Let's just forget about latency and just say we're going to get our 3 gigahertz. Fair enough? Okay. So the fastest between these two, just like the fastest theoretical speed between two dial-up modems years and years and years and years ago, fastest between our CPU and our memory is going to be the lesser speed of the two. Okay, so we got these two guys conversing at 3 gigahertz, which means that there's a slowdown. There's a bottleneck, right? Because our CPU wants it at 4 gigahertz, but it can only get it at 3 gigahertz. All right, now let's flip it a little bit. Go ahead.
I was just gonna say, well, wouldn't that necessarily be good for the CPU? Because if heat's our problem with the CPU, we wouldn't want that to be running at max.
Throw heat out the window though, because we got a good fan on there. So
Okay.
heat's not a problem. That's heat is a problem, and it's
But if you were like
the reason why we don't have faster than 4 gigahertz. Is really the heat issue. At 4 gigahertz, it's fine.
well, I'm just thinking like if you're trying to optimize your computer, if you had your CPU, you plan to buy one that's faster,
Yep.
say that it is, than your memory, that would actually be a good thing for you, right? Because if you're limited at what your memory can go, your CPU isn't going to reach a heat where it's actually going to destroy it, right? Or is that just like obvious?
I don't think that's necessarily true, and you'll tell us why in a few minutes. Okay. So now we were talking about a high-end CPU at 4 gigahertz, right? Now your new computer you just built. What's the clock speed on the CPU?
I think with turbo, it's like just a 4. So,
4. Okay. What's the standard without turbo?
It's
Like a 3.2 or something
yeah,
like that.
3, 4.
Okay. Now Van, you said yours is at 2.8, right? Okay. So let's assume that we have a 2.8 gigahertz Core i7 processor, and we have this 3 gigahertz RAM. Now the processor is actually the bottleneck, right?
Yeah.
Wrong. Processor's not the bottleneck. Why? Processor's at 2.8 gigahertz. RAM is at 3 gigahertz.
Can it split up the tasks?
No, they're gonna share RAM.
Who's sharing the RAM?
The CPU.
Today. You leave it without saying hi? Apology not accepted. You good?
I'm good.
Didn't you graduate?
No.
Oh, you're in Are you in capstone right now?
No. I'm going to be taking that in 2 semesters.
Oh, so you're not even close to graduating.
No, I'm like a year.
Oh, am I going to see you again? You could take 537? Oh, good. Did I send you an email, didn't I?
Yes.
You just didn't reply back.
I mean, well, I already told you in class I would.
You still could have replied back.
Yes, I did not. But I already told you in class I was going to do it.
Too rude, bro.
Too rude, bro.
So rude. But I mean, I'll definitely take it. So.
Because I'm going to make that class impossible. Even you won't pass. In fact, that's going to be my goal.
Which class is this?
He's in Masters of IT, MSIT.
Ah,
They have a second programming class in there, which is easier than our programming class in here
518.
because their focus isn't only programming. They have it's a hybrid skill. They're doing 75% using what's been created, 25% per creation. So this would be their advanced programming class.
538.
537. 535, 537 is their programming sequence. All right. All right, well, I'll let you go now. But it was good.
Well,
It was good. Oh, no, you can sit down. Grab a seat. It's good seeing you.
I'm gonna go get some tea.
Get some tea?
Yeah.
Oh, perfect. All right, take care. All right, so Van has a 2.8 gigahertz processor. Okay, so it can communicate at a maximum speed of 2.8 gigahertz, but he's running DDR4 at 3 gigahertz. So our initial logic would say that the processor is now the bottleneck because the fastest those two things can communicate, just like our old dial-up modems, is the slower of the two. So 2.8 gigahertz is the maximum speed that his processor can talk to that 3 gigahertz RAM. Yet, so we might say that the bottleneck, just barely, the bottleneck is actually the CPU. I'm saying it's not. The RAM is still the bottleneck. Why is that?
Does it come down to the number
It is
of
being
cores working on the
shared by
task?
multiple,
Shared by multiple what?
not only by processor.
It's shared by hard drive.
Okay, well, let's throw those out for right now. Let's pretend like it's not shared by anything else. And really, it's mostly used by the CPU. And we only need that comparison to make our logic work here.
Does the cores come into play?
Cores definitely come into play.
Okay. Well, is it because it's like the same example you gave at the beginning of the semester as well, like the number of people working on a task versus one person that can do it really fast? So like if he's only running that fast, he can also divide what's being transferred to, so there's slower speeds, but we also have four of them doing it at that speed, so therefore we're doing it 4 times the speed of that.
So here's a real quick real life example. Okay, we're on the cricket pitch. We're on the cricket pitch, right? Okay, we're on the cricket pitch. We got a big one of those water coolers up here, right? You know, you have your cup, you push the button to get the water come out. The water could come out at 3 gigahertz. Each of us players, so this would be what we have 4, 5, 6. So we have a 6-core processor out here. Each of you is operating at 2.8 gigahertz. Okay, so that means that you could fill your water bottle at 2.8 gigahertz. That spigot can spit it out at 3 gigahertz. Yet you're all trying to get water at the same time. That make sense?
Mm-hmm.
None of you are getting enough water. Right? Because now we have to divide that 3. If we assume RAM is giving each of you the same amount of time, we're dividing that 3 gigahertz by 6. So now we're at a half a gigahertz. So that thing's coming out in a drip.
Yeah.
You're trying to fill your water bottle. You can fill it up at 2.6 gigahertz, but it's coming out as a drip because it's only giving you 0.5.
Gotcha. Okay, so then do they divide the memory up? Is this eventually would they divide the memory up so that it has, say, like core type situation? So therefore, now each core of the memory is communicating to your CPU.
Okay, it's a good point. That's actually happened before. How many of you have heard of a processor called the AMD Opteron processor? Okay, the AMD Opteron processor. I had a motherboard that had a dual processor on it. So this is kind of before the dual core days, right before the dual core days. Each processor had its own memory bank.
Okay.
So they each got their own version of memory, but you had to physically had 2 separate memory banks to feed the CPUs. They talk to it separately. So you're kind of indicating that type of thing. Well, why don't we bump the amount of RAM? So bump the amount of the resource, but create a memory channel per core.
Yeah, right. The only problem is then you have to have something, you'd almost have to have like a CPU to sort out the information to what cores you want to use. I don't know.
Well, I don't know that that's true. Okay. Actually, no, you are right. Because the problem is so let's say that we have, let's say it's a 4-core processor.
Okay.
And let's say, just to keep things simple, let's say we have 16 gigs of RAM. So each core gets 4 gigs.
Okay.
The problem is that core 1 might need some data that's on RAM 3.
Right.
That he doesn't have a direct connection to.
Yeah.
See what I'm saying?
That's what I'm saying. It's like, would you have to have something where it's pulling it from the hard drive? So as it's pulling it, it's able to sort out what information is needed. Unless like you're in the program and you're running it and you need something that is already loaded to a different RAM stick, like, and it's on core 2 or whatever. But if you were able to, I don't know if it's just running a program, if you were able to do that.
Is that the Windows logo?
Yeah, that's pretty good. If you were able to like sort it out from the hard drive to those different cores to optimize how it's being run. I don't know if that would work or not, but
So these are our cores.
okay.
This is our RAM. All right. So the way this works, well, right now we might think of RAM as being one long stick of RAM. So here, let me just delete these guys just for a minute. So that's our 16 gigs of RAM. So even though you have two physical sticks, those guys are linked together, kind of concatenated. So you have this one giant street of RAM. And we'll talk more about that probably next class, and how it's actually organized on there physically, but relatively unimportant for us. All right, so this is your 16 gigs of RAM. All four of these cores are all competing over this one guy. That's the water bottle, that thing. So even though this guy's at 3 gigahertz, and each of these guys is at 2.8 gigahertz or something like that, okay, this guy's giving them their stuff at what, 0.75 gigahertz each? If he's equally balancing across the two, then you have the overhead of scheduling for that or whatever, blah, blah, blah. But let's not worry about that. The numbers are bad enough as it is, right? All right, so we might say, oh, well, instead of having that, why don't we go ahead and we can divide our 16 gigs of RAM into 4 pieces. All right, so let's say each of these pieces is 4 gigabytes now. All right, well, so now, and you can say that maybe 0 is linked to this guy, 1 is linked to this guy, 2 is linked to this guy, 3 is linked to this guy. All right, so they each get their own dedicated memory. Okay, so now we fix the blocking problem, because these guys are each 2.8, these guys are 3. So actually, now the CPU is the slight bottleneck. We can pretty much call them the same at this point, right? Okay, that's good. We're happy by that. Okay, so now the issue we have is if each of these is 1/4 of the whole. All right, we have a physical connection between the 4 cores and each of these, the fourths of the memory. Now we have the issue that core 0 might need something that's on memory stick 3, memory stick 2, I guess in this case, when he's actually directly linked to memory stick 0. So the data he needs isn't there. How do we fix that?
Well, that's where I was getting at. Is like before the memory stuff's loaded into memory, those 4 gigabyte sticks, it's like sorted out such that I don't know, maybe like one is like loader stuff, or one's like in charge of plugins. I don't know, just different stuff that wouldn't necessarily have to cross communicate across the.
Dedicated.
So kind of give each core a specific job.
Yeah, like this is your category of tasks. This is your category of tasks. So like each is in charge of their own tricks.
Okay.
So you can optimize.
You could certainly do that, but let's talk about a real life problem with that efficiency. Okay, so let's say that the 6 of you are doing some household chores. Okay, and Van is assigned one chore, you're assigned a different chore, so on and so forth. Well, let's say Van finishes his chore first. Unlikely, but let's just say he does. All right. Now, which is better? For him to sit on his butt and do nothing, or for him to pitch in and help somebody else with one of their chores?
Okay, I see what you're getting.
All right. So now you said, okay, well, we're going to solve the problem of our data not being there when we need it by just segregating the tasks. But now what we've done is we've reduced the efficiency of the CPU. Because one of the jobs of the operating system, so this goes back to Dr. Locklear's approach to the grand ideas of computer science. All of these different pieces are so interlinked. The job of the operating system, specifically the job of the process scheduler in the operating system, is to keep the CPU as busy, as close to 100% of the time as possible, right? Well, we got Van sitting on the sidelines.
but the CPU is linked together, so what would stop it from each core is initially in charge of each RAM stick, but they are linked, so what would stop it? So core 0 finishes, now it's computing with core 1 on that other memory stick.
Well, because in our model here, each of these memory sticks are effectively hardwired to a core.
Okay.
So
no
core 0, the spirit might be willing, but he can't access core 1's memory space.
Okay.
Make sense?
Yeah, I was just thinking, like, what if they could, though?
Okay. So you lose speed unless they're directly hard-coded to it.
Okay.
Okay?
All right.
So how can we accomplish the what if they could thing without having this guy directly connected to this? How can we upgrade this thing? So as of right now, do we see the weakness, the current weakness we have?
Yeah, because you're limited by the connections you have.
Okay. So actually, why don't we think about that?
Okay.
Let's take 10,
Okay.
and then we'll come back and we'll do our final hour, and you'll have the answer from when we come back, right? So you're gonna brainstorm this over 10 minutes. Okay, let's take 10 minutes.